When you see waves like that crashing on the shore, you quickly realize what tremendous energy they carry. In this program, we're going to look at how that energy is carried across the oceans. And to do that, we need to know how real ocean waves can be measured. We'll begin with a simple situation of waves in a laboratory tank, to remind you of the basic characteristics of waves that you read about in the unit. Water waves can be characterized by wave length, the horizontal distance from crest to crest, and by height, which is twice the amplitude. They're also characterized by period, the time required for two crests to pass a point, or by frequency, which is the number of crests passing a point in a given time, usually 1 second. In waves, the water particles move in nearly circular orbits, and at the surface those orbits have a diameter equal to the height of the wave. And you'll remember that there's little net flow of water in the direction of the wave. Beneath the surface, the orbits of the water particles become smaller. As this wax ball slowly sinks, it shows how the orbits change. They become progressively smaller, so that the effect of the wave becomes very small at a depth equal to 1/2 of the wavelength. A submarine at such a depth would be hardly aware of heavy waves on the surface. Well, where does wave energy come into all this? From your own experience, you'll know that large waves carry more energy than small ones. And I expect you'll remember from the unit that the relationship between wave height and energy is not a simple linear one. Energy is proportional to the square of the height. So by measuring the height of a wave, we can find out its energy. Well, that's fine in theory, but what about a situation like this? So many different waves are superimposed on each other, apparently in total confusion, that there's no obvious wave height to measure. Well, to begin to analyze this sort of situation, we need to go back to basics and to consider just two simple wave trains and what happens when they're combined. These two simple traveling waves have got nearly the same frequency. Now let's see what happens when we add them together. Well, you probably realize what's happening here. This is the formation of wave groups. And you should remember how individual waves behave in wave groups. What's the bright wave? It shows how each wave advances through the group and dies out at the front. Now let's look at that again. And that means that individual waves must travel faster than the groups. And in real water waves, exactly the same thing happens. And here the group speed is 1/2 of the individual wave speed. And for the propagation of wave energy, it's the group speed that's important, because that's the speed at which energy is carried by waves moving in deep water. But just look at this again. Which height would you choose to calculate the energy? Well, of course, you don't do it that way. We know that in this simple situation, these wave groups are made up of only two waves. So if we measured the heights and the frequencies of the waves in these groups, we could mathematically resolve them back into those two waves that we started with. And that's how we'd find the energy of the wave group. In the sea, the situation's more complicated, but it's just the same in principle. Wave heights measured over a period of time can be analyzed into the simple waves that make up those real wave groups. And once you've analyzed all the heights and frequencies, you can then calculate the energy per frequency and plot an energy density spectrum that looks like this. I want you to realize what it is that's being plotted. You've got energy over frequency plotted against frequency. And so the area under the curve represents the total energy carried by the waves. So here's how we can represent the energy of the sea surface after analyzing the real wave groups into their components. Well, now we need to recall another feature of waves in water. Different frequencies travel at different speeds. So let's do a little more revision. The speed and length of deep water waves is determined by their frequency. Low frequency or long wavelength waves are fast, and these cross the screen in 5 seconds. High frequency or short wavelength waves are slower. These take 10 seconds to cover the same distance. They're traveling at half the speed of the long waves. And you probably realize what this is illustrating. You're looking at an example of dispersion. To see dispersion, you can toss a handful of pebbles into a pool. Waves of all shapes and sizes are generated, and they'll spread out confusedly in all directions at once. As they leave the disturbance, the waves begin to sort themselves out. The long waves move out fast, and the short waves more slowly. Away from the disturbance, the confused surface has settled down. The waves are separated and regular, like swell in the oceans. And in the ocean, a storm has much the same effect as that handful of pebbles tossed into the pond. A storm gives a finite packet of energy to the sea, just as those pebbles did to the pond. But now let's try and see what dispersion does to such an energy packet after it's been delivered. I'm going to take a very simplified and highly idealized situation, and I'm going to assume that our energy packet is made up of waves of only 2 frequencies. And you'll see in very simple terms the effect of dispersion on that packet. When the 2 wave trains coincide, the packet has this shape. As the wave trains travel away from their source, the long wavelength waves move ahead of the short ones. And so at some later time, the packet will look different. And later still, dispersion has stretched the packet even more. Well, let's just look at that again. Dispersion's obviously changed the shape of the packet, but as far as the 2 components that make up that packet are concerned, their frequencies and their heights haven't been changed. And so the total energy of the packet can't have changed, even though the packet itself has been stretched. Well, now this idealized situation we can carry over to the real case where there's a whole range of frequencies. The packet will stretch out by dispersion, but dispersion won't change its total energy. And so the energy density spectrum measured over the whole packet will remain constant. Well, it would remain constant if there wasn't any loss of energy by interaction and attenuation. And we know that in the real sea, interaction and attenuation happen to waves. Now, in 1963, Dr. Walter Munk and his colleagues of the Scripps Institution of Oceanography in California wanted to know how and where that attenuation of storm waves actually happened. So they devised a classic experiment using the biggest wave tank in the world, the Pacific Ocean.
The waves that come onto the beach here in La Jolla may have come from very distant storms. Of course, it's not an individual wave crest which you can follow from the storm, but rather an energy packet. The way these energy packets propagate and attenuate was the subject of a fascinating expedition some years ago. About a dozen years ago, theoreticians became worried about waves interacting with themselves. But there was no experimental evidence. So we thought we would set up an experiment taking advantage of the fact that ocean waves travel over very large distances and are attenuated precisely as a result of such wave interaction. We therefore occupied a series of stations all the way from the southern oceans to Alaska, putting special emphasis onto the equatorial region where these waves would cross the trade wind sea. Let me show you where the experiment was set up. Here's the Antarctic continent, the southern oceans, where the severe storms take place during the southern winter, and the waves come from these storm areas and travel up into the Pacific Ocean. We wanted to select stations which were along a straight line from the storm, known as a Great Circle route. At the same time, we wanted to avoid any island chains which would cast a wave shadow and interfere with an attenuation study. For each of the sites, we wanted to place the station where it was most exposed to the incoming waves from the southwest, and to place the instrument sufficiently offshore so that the effects of refraction and the effects of shoaling on wave height would be very small. Here are the stations that were selected. The first station in New Zealand, almost in the tail end of the storms. Further north, American Samoa. Palmyra, just north of the equator. Hawaii. And the last station in the Gulf of Alaska, Yakutat. And in between Hawaii and Yakutat, we placed the Scripps floating platform flip. We want to measure wave height offshore. And an easy way to do this is to measure the pressure on the seabed due to the waves passing overhead. We do our recording on the island, run a cable offshore, and then connect it to a pressure transducer. This is it, and the key element is the Vibrotron transducer shown here.
A thin tungsten wire is mounted in a cylinder between a rigid base and a diaphragm. The wire vibrates. As the water pressure increases under a wave crest, the diaphragm is depressed, the tension in the wire is slackened, and the frequency of vibration reduced. The wire oscillates in a magnetic field inducing a fluctuating current. This electrical signal is amplified, transmitted, and recorded. In Alaska, our recording instruments were to be housed in the Coast Guard station at Yakutat. A fishing boat, operated by an Eskimo crew, took Gaylord Miller out to the spot selected where the water depth was 60 feet, deep enough so that the waves had not yet been substantially affected by the bottom. The tough problem was to get the cable ashore. The line fired up onto the beach was used to pull the cable from the wave sensor to shore. The wave sensor, mounted on a quadrupod, was lowered into the sea in the spot marked with a buoy. The recording equipment on shore could now be connected. In Samoa, the problem of installation was simpler and warmer. First, we laid a cable from a nearby village to a rocky point. There, a narrow underwater crack in the rock with a sandy bottom was a naturally protected place to lay the cable. The cable would have to withstand a full summer of buffeting from the pounding surf. The wave sensor had been lowered into the water from an outrigger beyond the breakers. We had to hurry to stay with our schedule. Winter was descending on the Antarctic. Studying the weather maps of July 5th, Bill Powers noted a great storm building up south of New Zealand. This storm would impart energy to the sea and create the wave trains we wished to study. However, New Zealand on July 6th, the waves from this storm arrived. The station had gone into operation just one day before. At last, our instruments could measure some real Antarctic waves. Frank Peterson, in charge of the New Zealand station, was pleased to note that the wave sensor was working smoothly. Each 2-second reading gave a sample of the wave height measured to the nearest 10th millimeter. We had all gotten pretty good at reading the tape code. It gave us the advantage of an on-the-spot analysis of the waves. This is a plot of the sea surface against time. The profile is irregular. At New Zealand, the period was measured at 16 seconds. The corresponding group velocity was 27 miles per hour. In Samoa, it was the arrival of the wave group that interested us. We were not trying to identify individual waves. To operate our recording equipment, we had taken along our own generator. As at all the stations, we recorded for 3 hours, twice each day, from 4 to 7 a.m. and from 4 to 7 p.m. Preliminary analysis showed that the waves at Samoa were more regular than at New Zealand. This is because the long waves, which move rapidly, have separated from the short waves, which are slower. Flip had arrived at her lonely North Pacific station on her first major assignment at sea. The wave sensor had been bolted to the hull of Flip and would reach the proper depth when Flip flipped. As the strange ship floods her ballast tanks and slowly tilts to her vertical operating position, all but 55 of her 355-foot hull sinks underwater to form a surprisingly stable base of operation. Flip is designed to heave up and down at a natural period which is longer than the longest swell. Consequently, she barely moves with waves, only 3 inches in a 30-foot sea. As she flips, the crew aboard shifts with her, walking now on what before were walls and rails. Jack Northrop operated the wave recorders aboard Flip while she was on station for a month. Wave measurements aboard Flip were comparable and in some ways better than those on land. Flip floated with negligible drifting, taking wave measurements for 3 hours, twice a day. After a 10,000-mile journey across the world's largest ocean, our waves, direct descendants of the waves born in the Antarctic winter, finally reached the shores of Alaska. Here, after their 2 weeks' journey, they finally die on the gently sloping beaches. The energy which had traveled across half the planet is at last expended in the breakers. It was here that our data would, we hoped, tell us how much of that energy had been lost in transit.
Well, that's the experiment. Now let's look at just what it was that Walter Monk and his colleagues were measuring. Well, first of all, there are always waves in the sea, so that at any one station, Honolulu for instance, the wave recorders would still be registering the general background wave activity, and that would give you an energy density spectrum looking something like this. Its general shape would vary and fluctuate, of course, from hour to hour, but overall it would stay much like this. We say a bit more about the details of that shape in the broadcast notes, but let me just tell you now the frequency from 0 to 6 cycles per minute, and here, of course, energy over frequency. Now, what we want to look at now is how that spectrum would change as the energy packet from the storm began to arrive. And you'll need to remember 2 things. The first, that the wave recorders were run for 3 hours in every 12, and the second thing is dispersion, which means that the low frequency, long waves would arrive first because they moved faster, and so they'd be recorded first. So let's think about how that would affect our energy density spectrum. Now, those first arrivals would be expected to add a peak to the energy density spectrum at the low frequency end. Something like this, in fact. And that peak there represents the energy added by the first waves to arrive from the storm. Now, we've actually got the computer results for those early arrivals. Here's the first one. And because of dispersion, at each successive recording, the peak moved to higher frequencies as the shorter and slower moving waves passed through. And I've built that up in 3 dimensions here, which means that now we've got the time axis. Now, you remember the recordings were made every 12 hours, and so you've got 2 sets of readings for each day. And the major effect of the storm passed through Honolulu in just 4 days. And as I said before, these peaks represent the extra energy added to the sea surface by the storm. Now, you can do this for each of the 6 stations. Let's just see what Alaska looks like. Well, the effect of dispersion shows up very well. The storm energy was still passing through after 6 days when they stopped recording. Dispersion's obviously stretched out the energy packet even more. But dispersion wasn't the primary objective of this experiment. What Monk and his colleagues were really interested in was the way that this storm energy changed between stations. Where did the attenuation happen, and how did it happen? Now, we can get an idea of that by drawing a smooth curve through these peaks for each of the stations, and then comparing those curves for each station. But let Walter Monk tell you about it in his own words.
This graph sums up the expedition result, makes it a little simpler than in fact it was. Here's a frequency axis going from low frequencies of about 3 cycles per minute to about 6 cycles per minute. And this is the energy density associated with these frequencies. Now, take New Zealand first. On a given day, early in the storm, we would get a low-frequency spectral peak like this. A day later, the peak has wandered to higher frequencies and may look like this, simply because the high-frequency waves move slower and come in later. And if you now plot a curve through the peaks of this wandering spectrum, you get the curve marked New Zealand. Now, similar things happen at the other curve, at the other stations, Samoa, Palmyra, and going north, only that these peaks come in somewhat later because the stations are further from the storm. Now, what are the results? At low frequencies, all the stations are on top of each other, meaning that there is no measurable attenuation as expected. At higher frequencies, we found to our surprise that nearly all of the attenuation took place between New Zealand and Samoa, and from Samoa on north all the way to the Arctic, there were virtually no measurable attenuation. This meant that the wave interaction was much more severe in the near storm zone than it was, for example, when the waves crossed the equator, where we had expected to find the major attenuation. Actually, on hindsight, this makes very good sense, because in the near storm area, where the waves are high and steep, they interact much more strongly than further north, where they have sorted themselves out and became lower and weaker.
That experiment was done in 1963, and it's become a classic in physical oceanography. Oceanographers now have got a much better idea of just how the energy of storm waves is attenuated. And as Walter Monk himself said, the experiment also demonstrates that theoretical predictions can be wrong. The equatorial attenuation that they expected did not happen.